Okay, so thanks for your introduction. So my name is Liang Wenyu from I2R, Robotics and Autonomous System Department. So today my topic is about robot manipulation using multisensory feedback. Okay, so now we see all the demos outside and also some talks the speakers given. So most of the sensor we use on the robot or with the robot is vision. Okay, but the problem is successful manipulation only use vision is not enough. This is because we have different properties in different objects, right? So we have shape, rate, COM, that means center of mass, also the surface properties. Okay, let's imagine. So we have two bottles, all transparent. One is plastic, one is glass. Okay, only use vision, what it can do, right? So when we do a grasping, if we apply the wrong force on the plastic bottle, it may fail. Okay, so it's very important. And also we have uncertain visual models. Okay, so we always have uncertainties on this kind of image processing or the models trained by the vision only. Okay, the most important thing is intrinsic properties of an object, like the mass distribution, are very difficult to learn by vision only. Okay, so here I give an examples. So you can see this T box. Okay, inside the T box is not full of it; it's only half of it. So in this case, the COM is not in the center, right? So let's say if I only use vision to grasp this T box, it will fail, because when we use camera only, we will think about, or we thought that the COM is in the center only. Okay, but actually it's a bit off. Okay, and also another example is for the pushing. So if you push this kind of T box, it's not able to push the box translationally if we rotate. Okay, this is because the COM is wrong by vision. Okay, so we need to find out a solution, right? Okay, so to address all these challenges, physical interaction with object is essential. Okay, such kind of interaction like human, like what we do on the object manipulation, it allows the exploration of objects' intrinsic properties. Okay, so when we do the grasping on the T box, we try to use our skin to feel the COM, right? And also our vision also. Okay, so tactile sensing provides rich touch information that can be used to obtain a wide range of object level information. Okay, so it's like what humans do on the grasping on manipulation. So our solution is, how about we enable the robot to have the sense of a touch, and we use this kind of information together with the vision information to achieve the successful manipulation. Okay, so I will talk about two of our main work related to this kind of multisensory feedbacks based manipulation. So the first one is visual tactile feedback based robot manipulation. This is a work for the object packing problem. Okay, so first of all, let's take a look at the hardware system. So we need to enable the robot have the sense of touch like human. So we need to give the robot have the skin sensor, right? So here we have the tactile sensor on the gripless fingertip. One is in the inner side of the finger, another one is outer side of finger. So this one is for the grasping, and then this one is for the pushing. Okay, so of course we still have the camera system, so we still need vision. Otherwise we are blind, right? So we have the eye in hand camera, and then we have force torque sensors on the wrist of the robot. Okay, so we have three different tactile sensor or force sensors with the robot. And then based on this hardware, we propose a manipulation planning framework with a multisensory feedback. Okay, so this is some details about our framework. Okay, so in order to achieve the successful manipulation, so that means we want to grasp the object stably and also push the object translationally. So we have proposed a framework in this way. So we have two parts. One is the multi-affordance representation learning model with a built-in attention mechanism. Okay, so this is how the this affordance model looks like. So we have the touch information as the input. We also have the image as the input also. then affordance type, and also we have the previous exploration results as another input to the model. Okay, with all this information, then we will generate a kind of affordance map. Okay, this map is to show the manipulable locations of an object. Okay, that means it will show the robot where is the correct location for stable grasping or for translational pushing. Okay, and this is with attention mechanism here. This is to let the system to pay more attention to the previous exploration manipulation locations. Okay. Okay, so to further improve the efficiency and accuracy, you also have a RL here, the reinforcement learning pipeline, together with our affordance model. Why we did this one is because if you only use the affordance model, you will need multiple times of exploration on the object randomly. Okay, it may take times, right? It takes several times to try on the objects. That's why we try to use the RL method to speed up, to reduce the number of the exploration. Okay, so this is the overall framework, how the overall framework looks like. And now I want to show some results. First of all, let's have a look at the affordance model results, right? Okay, so we have used the building blocks to build different shape, to represent different shape of objects. And inside the building blocks, we will try to mount, install, or put some weights on different location to simulate the objects with different COM. Okay, so this is the objects we use. We have the I shape, L shape, T shape, and also cross shape. Okay, here is some results shows on the of this model output. Okay, let's take a look at the results on grasping. Okay, so is from these results or these numbers, it shows that our proposed model, we call it TAGN, can make more accurate predictions on appropriate area of stable grasping. Okay, so it can always output the correct grasping position to the robot. Okay, and if we look at the results on the pushing, okay, so the AGN here means we don't use tactile sensor, and the TAGN here we use tactile information. Okay, so this is very interesting results. So you can see once we have the tactile information, our model can perform very good predictions on the correct position location. Okay, so it's about 30% better than result using the tactile information. Okay, so here is the outputs from of the affordance map for the pushing task. Okay, then we can use the affordance model output to directly to input to the robot to conduct the manipulation task. This is a video to show how we can use the affordance model to perform the task. So here is only the vision-based policy, and the second one is vision plus force torque information, the force torque sensor, and this one is all the information, including the tactile information. So obviously, for the vision-based policy, it only works well or correctly for the objects with uniform mass distribution. Okay, this is for sure. And for the vision plus force torque, it can help the system to do stable grasping quite good, but the problem is it's not works well in push avoidance. That means for the pushing, it's not works well. But when we have our sensing information, it performs the best. Okay, so this is we only use affordance model to do the manipulation. Now we try to include the RL here also. Okay, so this is the comparison. This table shows the comparison results between the methods with and without RL. Okay, have RL here, that means we have the RL pipelines into the system. So our proposed method can achieve the best success rate. Okay, I try to speed up. Okay, and okay, so if you look at the results comparing by the RL only use 2 exploration and the operating model use 5 exploration, you can find out that, oh, now we only use 2 exploration. When we use the RL, then we can achieve the same accuracy or higher accuracy than a model using affordance map only, but it's five times of exploration. That means using RL here can further or greatly improve the efficiency of the overall framework. Okay. So we also test our framework on the real world objects. This T box full with T bags inside and half of it, and also the 2-page box, and also on the message gun. This is the results. So it shows that the successful rate can be up to 85% in the manipulation tasks. And here is a video to show the use case on using our framework in object manipulation. So we can use this framework to try to explore where is the stable grasping location, where is the translational pushing location. Then we can do the manipulation together. Okay. So this is on the building box, and then we also work on the real world objects. This is a kind of a dense object packing task. Yeah, so with our framework, it's successfully to place this T box inside the bigger box correctly. Okay. Okay, so let me talk about another of our work presented in the KUKA Innovation Award. So it's called Robot Task Execution with Vision and Tactile Sensing. Okay, so slightly different. The work here, this work is to enable a robot manipulator to perform accurate actions with long fixed configurations. Okay, and the setup is a little bit different. So we have a eye-to-hand camera and eye-in-hand camera, and also the tactile sensors here. So for the eye-to-hand camera, is a kind of global camera to give the robot to have a sense of where is the object is. Once the object is localized, then the robot arm will move on top of the object and then use the eye-in-hand camera to further estimate the location of the object. Okay, then we will do a grasping. Okay, and why we did a tactile sensor is because there are some uncertainties on the eye-in-hand cameras, right? So when we do grasping, it may be off. That means the assist of the input shaft or the object is off of the gripper. So in this case, we have a kind of 5-key information from the tactile sensor for the object grasping position estimation. Okay, so here is some tactile sensor outputs to show the relations between the offset of the grasping position and the tactile sensor output. So based on this 2 information, we can localize the objects, identify the grasping position, and then we can do the insertion correctly. Okay, so these 2 figures shows that if, let's say, the grasping position is different, how the tactile sensor output looks like. Okay, and here's a short video to show the object insertion in an assembly task using the visual tactile feedback. Yeah, so we will use the global camera localize and further use the eye-in-hand camera to locate the input shaft. Okay, almost done. Location, then we do the insertion. Yeah, so with with all this multisensory information, we can successfully insert the input shaft on the casing box, the casing base here. Okay, so we also use our system for the input shaft handover. That means handover task. So we use a global camera, the eye-to-hand camera, to roughly detect the hand-object relations. So once there is the hand overlap with the objects, so maybe the system can realize that, oh, someone is taking the objects like this, And we further use the tactile sensor information to confirm whether the object is catched by a human. Okay, so this is input shaft and over task. Okay, so it's a conclusion. So in summary, we have developed multisensory based object manipulation pending frameworks using multi-affordance model and RL for manipulation tasks of objects with unknown intrinsic properties. We have tested our frameworks in different experiments. The results shows that the proposed method achieved better accuracy, especially for the push avoidance prediction. And the proposed framework can also achieve the manipulation task with a very high success rate and high efficiency because the RL pilot here. And we also use the vision tactile sensing information for the robot task execution. We have done the object insertion and handling with the help of the vision sensors and the tactile sensor to remove the need for detailed calibration, predetermined objects position, and the risk for the enormous or unsafe execution. Okay, so this is two reference we publish. One is the IL paper we just published this year, and the other one is the ICSR papers we published in 2021. Okay, I think that's all. Thank you.
Any quick questions for Dr. Liang?
Okay. The first question is Dr. mentioned that you collect data set. So may I know what is the scale of the data set you build up by yourself? The scale. You mean the numbers, right? It's about 3,000, 2,000, 3,000. That one, yeah. Yeah, good point. Maybe, yeah. Because our data set is on the building blocks. The building blocks, so it's not the real objects. So later we try to work on the real objects, then maybe that data set is more meaningful. Yeah. So maybe I will release that data set. Yeah, we are working on it now. Yeah. Okay, so we still use the same affordance model, but we don't have the touch information as the input. So we still use the affordance output to estimate where is the grasping point. Yeah. Yeah. No. No. Okay. Thank you.